Okay, I want to briefly go back to the very end of the previous video, so video 5, because I think that the way that I described that very last part might have been confusing and I wasn't able to edit it and change it. So let's say we have, I'm just going to use an even simpler example. Let's say we have this constitution. There are two asymmetric carbons in it. So the maximum number of stereoisomers is 4. So what we see, not even envisioning any stereochemistry, is that there could be a situation where if we rotate around that bond, we're going to get to a picture like this, a conformation like this, with the potential for an internal symmetry plane. Okay, so that has to be true if you're going to have a meso compound. There has to be that internal symmetry. The stereoisomer of this constitution that will be the meso compound, the absolute configurations on those two carbons will be opposite one another. So one will be R, the other one will be S. By contrast, the chiral members, so the two enantiomers, just like we looked at in the previous example, in the previous video, will be RR and SS. So that's one thing you can do. You can also, if you're looking at a structure and trying to decide whether it's a meso compound or not, you can just draw the mirror image and see if it's superimposable. So just another thing to think about as you're looking at these structures in different ways and using different approaches. Bottom line for all of this is that when you're comparing two structures, it's really, really useful to assign R and S. So let's make a little list and then we'll go ahead and finish the rest of the packet. When you're comparing two structures, typically the question involves what's their relationship? Are they identical? Are they constitutional isomers? Are they enantiomers? Or are they diastereomers? So the first thing would be to rule out constitutional isomers. So take your two structures and make sure that the connectivity is the same. If it's different, they're constitutional isomers, and you're finished. Assuming the connectivity is the same, you would go ahead and look for asymmetric carbons. So find your asymmetric carbons and assign absolute configurations. We'll just say assign R and S. Then you can compare the two structures just using the absolute configurations. It's a lot quicker than trying to make models, trying to redraw things, draw them upside down, flip them over, rotate them, whatever it is that you're trying to do. Just assigning the R and S gets you into it very, very quickly. So then compare your structures using your R and S assignments, just like we did for the two examples in the previous video. Okay, so let's wrap up our discussion of stereochemistry by looking at something called optical activity. To understand optical activity, first of all, we have to appreciate the fact that any pair of enantiomers is going to have exactly the same physical properties. So remember, the characteristic physical properties of a compound are things like the melting point, the boiling point, the density, refractive index, and so on. So they're all the same for a pair of enantiomers except for one. And that is probably not something that's been on your radar. That is the rotation of plane polarized light. So I'm going to abbreviate that as PPL. That's just for our notes. That's not how it's abbreviated everywhere, but just so that you don't have to write that out every time, and I don't have to write that out every time. So what is plane polarized light? Okay, so let's imagine a light source, like this really strange looking light bulb. Let's make it into a light bulb. There we go. Okay, so here's a light source. And light is emanating and traveling in all planes from this light source. So if you allow the light to pass through what's called a polarizing filter, the polarizing filter has these slits in it that are called gratings. The light that makes it through is all traveling in the same plane. So that's what's called plane polarized light. Okay, so let's say now that you have a sample of plane polarized light, or that you have plane polarized light, you allow that light to pass through a sample. It's going to be a pure sample of a chiral molecule. So this is in some kind of a sample cell, and the light passes through it. The light is able to interact with the chiral molecule in such a way that the plane is rotated. So what we can say, chiral molecules rotate plane polarized light. And this ability is called optical activity. Okay, so let's say a sample, whether it's pure, so a pure compound, so just one thing, or a mixture of things, a sample that rotates plane polarized light is optically active. But by contrast, a sample, again, whether that's pure or a mixture, so one compound or more than one compound, that does not rotate plane polarized light is called optically inactive. Okay, so how do we know whether this is going on or not? So what we do is we do an experiment using a piece of equipment called a polarimeter. So a polarimeter is an instrument that measures optical activity. Okay, so let's say that we have a sample. So our sample is in this little sample cell down here. And we are introducing plane polarized light coming in this direction. Okay, so the light passes through the sample, and then it's going to rotate. So it can either rotate from the point of view of this schematic in a positive direction. That's called dextrorotatory. Or in a negative direction. That's called levorotatory. So we measure the direction and the magnitude of the rotation of the plane polarized light. Now, there are some other notations that you might see, especially if you take biochemistry. So a small scripted L and a small scripted D, a minus and a plus, or small caps L and small caps D. Okay, now, some of these have physical significance, others do not. For example, this down here is older notation that's used for carbohydrates. But the reason that I point these out is that you may see these, and so now you know what they relate to. They relate to optical activity. The plus and minus in particular relate to how the plane is rotated once it passes through the sample of the chiral molecule. Okay, so let's look at some other ideas relating to this. Okay, so here we have a pair of enantiomers. Now these are the enantiomers of 2-butanol. And so because there's only one asymmetric carbon, we only have one absolute configuration in each of the structures. And the one on the left happens to be R. I'll leave it to you to figure that out or to confirm that, which means that its enantiomer is S. Now, you can show in the name, if you know it, if you've done the experiment, you can show the plus or the minus. So incorporated into these names is the negative and the positive. That's telling you which direction the plane polarized light was rotated by the sample. Now, minus does not necessarily correspond to R, and plus does not necessarily correspond to S. So there's plenty of examples where it's S minus something and R plus something. So remember, R and S are just arbitrary. It's based on a system of naming rules that somebody came up with, or actually 3 guys came up with, and has nothing to do with anything physical, whereas the plus and minus do. Now in this case, for the butanols, we have these numbers. And these are the actual magnitudes by which the plane polarized light was rotated. So each of these is referred to as a specific rotation. So these are the specific rotations. So each chiral compound is going to have a specific rotation associated with it. Now notice with those numbers, a pair of enantiomers rotates plane polarized light in equal and opposite directions. So this is the only difference in their physical properties. Okay, so now suppose you have a pair of these enantiomers, or any pair of enantiomers, and they're present in equimolar amounts, meaning equal number of moles. Remember that we call that a racemic mixture. So a pair of enantiomers present in equimolar amounts, so same number of moles, is a racemic mixture. So let's say that you put your racemic mixture into the sample cell in the polarimeter and you measure its optical activity. Let's say that it's these 2 enantiomers that we have up above on the screen. So the R2-butanol is going to be rotating the plane polarized light that's coming through the sample negative 13.5 degrees, but the S2-butanol is going to be rotating it positive 13.5 degrees, meaning that the effects cancel and the mixture is optically inactive. So a racemic mixture is optically inactive. But if you have just a little bit of one enantiomer over the other, then that mixture would be optically active. Now, it's not right to say that a racemic mixture is achiral, because the terms chiral and achiral and meso, those describe individual molecules. So a racemic mixture contains more than one molecule, and so we can think about it as being optically active or optically inactive. In this case, it's optically inactive, of course, but we cannot describe it as achiral because this is a term used to describe a single molecule. Now the last question here, how do we get a racemic mixture? As it turns out, that's going to be as the result of a reaction. So we're going to be looking into the details of that as we start our next sections in the gapped notes, which deal with organic reactions. So we've now completed all of the structural information and all of the things about orbitals and bonding and stereochemistry that we need in order to understand the outcomes of reactions and how reactions occur. So we'll look more into racemic mixtures once we get there. One more thing that I want to point out to you is that in the objectives, these are all still pretty good, except that we're skipping the Fisher projection, so you don't need to know how to draw a Fisher projection for a molecule, so you can strike that, but everything else is good to go.